Welcome to Pod Talk, where we break down complex Kubernetes topics into bite-sized, visually explained lessons. We go beyond the theory and show you exactly how it all works, with easy-to-follow demonstrations. Let's get started. Have you ever wondered how containers talk to each other inside a Kubernetes pod? Today, we're diving into the fascinating world of pod networking to understand exactly how this communication works. Let's explore the seamless connectivity that makes Kubernetes pods such a powerful concept. At its core, a Kubernetes pod is the smallest deployable unit in the Kubernetes ecosystem. Think of it as a logical host, a cozy digital home where containers live and work together. Each pod can house multiple containers, and these containers are designed to operate as a cohesive unit, sharing resources and working in harmony. Here's where it gets interesting. Containers within the same pod share something special. They share the same network namespace and IP address. This means they can communicate with each other using localhost, just as if they were processes running on the same computer. There's no need for complex networking or external connections. It's all happening right there inside the pod. To better understand this concept, think about how programs communicate on your laptop. When you have multiple applications running on your computer, they can easily talk to each other because they're all operating within the same system. That's exactly how containers in a pod work. They have direct, efficient communication channels between them, making data exchange quick and seamless. In this hands-on lab, we'll explore how containers communicate in Kubernetes. We're going to demonstrate two different approaches. First, we'll see how containers in separate pods communicate over the network using IP addresses. Then, we'll discover the power of co-located containers, containers that share the same pod and can talk to each other using localhost. If you don't have a home lab or a virtual machine spun up, that's totally fine. This lab is designed to be run in a killer shell or killer coda environment. It's a very fast, convenient way to use a real Kubernetes cluster for a limited time to practice what you've learned. Let's dive in. First, let's make sure we're connected to a Kubernetes cluster. Perfect. We have a working node. Let's also check if there are any pods currently running. Great. We're starting with a clean slate. No pods are running yet. Now we're ready to create our pods. Let's create two separate pods, one running an Nginx web server and another running a curl container as our client. Great. We've created two independent pods. You might notice we use the sleep 3600 command for the curl container. This is actually a best practice when working with utility containers. Here's why. The curl image is a toolkit designed specifically for making HTTP requests, but it doesn't run a service like Nginx does. Without giving it something to do, the container would start and immediately exit. The sleep command tells it to stay alive for 3600 seconds. That's 1 hour, which gives us plenty of time to exec into it and run our tests. This is the standard approach for keeping utility containers running in Kubernetes. These pods are not co-located. They're completely separate with their own network namespaces. Let's check our pods and see their IP addresses. Perfect! Notice that each pod has its own unique IP address. Make a note of the web server pod IP address. We'll need it in just a moment. You can see they're completely separate network entities, each with their own IP. This is what we mean by non-co-located. They're independent pods. Now let's see how containers in different pods communicate. We'll exec into the client pod and use curl to reach the web server using its pod IP address. Replace this IP with the one you noted earlier. Success! You can see the Nginx HTML welcome page. The client container was able to communicate with the web server container by using the pod's IP address. This request went through the Kubernetes cluster network, from client pod across the network to web server pod. So, this is how containers in different pods communicate. They use pod IP addresses and send requests through the cluster network. This works perfectly fine, but notice, we had to look up the pod's IP address. The communication goes through the network stack with routing and forwarding. If the pod restarts, its IP address could change. There's network latency and overhead. For containers that don't need tight coupling, This is the right approach. But what if our containers need to work together closely? Let's clean up these pods. Now, let me show you a better approach for containers that need to collaborate. When containers need to work closely together, like an application and its log collector, or a web server and a monitoring agent, we collocate them in the same pod. Let's create a pod with 2 containers using YAML. Perfect! We've created a single pod containing 2 containers, a web server and a sidecar. The key difference here is that these containers are collocated. They're inside the same pod and will share the same network namespace. This is a common pattern when containers need to work together. Let's verify our pod is running. Great! You can see 2 hats containers are ready. Now let's check the pod's IP. Notice there's only one IP address for this pod, even though it has 2 containers inside. Both containers share the same IP address because they're collocated in the same network namespace. Now here's where the magic happens. Remember in part 1, we needed to look up the pod IP and send requests through the network? Watch how much simpler this is with collocated containers. Let's exec into the sidecar container and try to reach the web server. Now we're inside the sidecar. Let's connect to the web server using localhost. Amazing! Look at that. We got the Nginx welcome page using just localhost 80. No IP address lookup needed, no network routing. The sidecar container reached the web server instantly using localhost because they share the same network namespace. Let's exit. This is the power of collocation. When containers are in the same pod and need to work together, they communicate via localhost, no IP addresses to track or manage. Communication is instant with 0 network overhead. It uses the loopback interface. It's simple and intuitive, just like programs on the same computer. Kubernetes guarantees they're scheduled together on the same node. They restart together as a unit. This is why Kubernetes uses pods as the fundamental deployment unit. The pod abstraction allows tightly coupled containers to work together seamlessly. Think about real-world examples. An application container that writes logs with a logging sidecar that reads from localhost to collect and forward those logs. Or a web application with a caching proxy on localhost for instant access. These containers need fast, simple communication, and collocation makes it possible. This is ideal because oftentimes containers need to work together inside pods, and localhost communication makes that collaboration fast and efficient. So what have we learned today? Kubernetes gives us 2 ways for containers to communicate. When containers are in separate pods, they're non-collocated, they use pod IP addresses and communicate over the cluster network. This is perfect for independent services that don't need tight coupling. But when containers need to work closely together, we collocate them in the same pod. Now they can use localhost for instant, simple communication with 0 network overhead. This is the Kubernetes way of grouping related containers that need to collaborate. Thanks for following along with this lab. I hope this hands-on demonstration has shown you the power of pod networking and why collocated containers are such an important pattern in Kubernetes. Until next time, keep your clusters running smoothly.